I'd just like to hand over to Nick.
Hi, everybody. Welcome back from lunch. I wanted to say thank you to Nikolai for giving a really good architectural overview of Android. I've actually been through 2-hour-long presentations on pretty much every topic that he covered. So to cover that much material that quickly is really impressive. Anyway, first of all, I want to introduce myself. Who am I and why am I here? So this is a pretty picture of me. My name is Nick Kralevich. I've been a member, I was one of the founding members of the Android security team when Android was really small, when it was first really starting off. I've been working on Android now for almost 7 years, focused full-time on security efforts. The Android security team is really diverse. We cover a lot of different things. Malware analysis, reverse engineering, stats and analysis, looking for bad behavior, patching the device, trying to break into the device. My job is platform security lead. So what does that mean? That means basically I am responsible for all the security properties of all the code that runs on the device. The security model, understanding how that interacts with the other parts of the system, understanding how that impacts malware, overall trying to keep our users safe. And also setting standards for the industry to try to figure out what are the desirable security characteristics we want to see in Android, or what are some of the undesirable security characteristics we want to see in Android. In my role, I actually have the opportunity to touch billions of people. I remember when I realized the change I had committed to the Android code base was running on over 1 billion devices. It was a really good feeling. But I'm just one of many people that actually work on Android on a day-to-day basis. Android itself is a huge project, certainly more than even just the team at Google. Millions of lines of open source have been contributed to Android from developers who may or may not care about security. Security may not be the first thing on their mind. The people in this room are security experts, but other people are GPU experts, compiler experts. And this is all code that we've made available. One of the beauties of Android is the fact that everything is open source. People in this room can go into Android and get a really solid understanding of why Android works the way it is. Look at the history, look at how we've changed things. And I think that's one of the strengths of the Android ecosystem, that if people want to, they can understand what's going on, they can understand and modify it. During Andrew's presentation today, it was impressive to me just how he took Android, added logging, added instrumentation to it, and is able to derive a lot of characteristics about Android applications. And these are the kinds of innovations that we want to see. Thousands of devices have chosen to use Android, and something I'm really proud of. And there are literally hundreds of companies out there that are focused on security efforts for Android. And everybody in this room is in one way or another involved in Android security. And so it's something that is really impressive to see. But I want to step back a little bit and talk about fundamentally what is security? What does it mean to be secure? Everybody in this room has a different idea of what it means to be secure. There's a popular joke in the for computer security practitioners that the only safe computer is the one that's unplugged. Sadly, that's not even, after my coworkers looked at this slide and they go, Nick, you know, that's not even true for Android. You have batteries on the device. You can't unplug an Android device. And I'm like, oh, nuts, another security hole. Anyway, the first lesson, you know, one of the goals I have today is to try to distill lessons, things that we've learned from Android security that I think are applicable to the wider community. But the first lesson that I want to convey today is really fundamental. Everything that we do in security is to some degree a compromise between security and functionality. When we enable something, when we let people use their devices, we're implicitly giving up some control over them. We've been fortunate in that Android has had years to try to figure out the right compromise between security and functionality. It's not something that we always get. It's not something that we always get right. It's a continued work in progress, and trying to find the right balance is hard, and it actually varies on a per individual basis. We'll step back a little bit, and I want to explain some of the core things that drive our thinking and what we're hoping to accomplish. A lot of times when you think of security solutions, this is the picture that comes to mind. You have the security guard who's there, the big signs, something bad has happened. The classic example I think of is firewall software that's installed on PCs. They pop up an alert, oh my goodness, your application is trying to connect to port 80. But it pops up the alert to try to tell users, hey, something might be wrong. And to some degree, doesn't try to, but it has the effect of instilling fear within the user. Plus, a lot of times, this fear isn't necessarily well-founded. It may not be the right kind of decision-making. A lot of times, these are also minimally effective. They catch things which are benign behavior, don't catch things which are things that people really should be concerned about. Android has a different philosophy when it comes to security. The most effective security is invisible. And just by running an Android device, you should feel a sense of calm, that even if you take whatever actions you take, your data, your confidential information is going to be secure. And so this has been the guiding philosophy behind Android. We try to make sure that the properties that Android have are secure by default, that we protect users right off the bat. And we don't force users to make unnecessary decisions where they don't have to. So how do we actually do this? How do we actually bridge the gap and try to make it so we design a system where security is forefront, there's active involvement in security, people feel protected, but people aren't consciously involved in it. When my mom runs Android, she shouldn't have to make decisions. Is accessing dev null safe? Well, somebody else has made that decision for her, and hopefully it's the right answer. How do we bridge the gap? Today, I'm primarily going to focus on the lower right-hand corner, talking about runtime security, talking about our sandbox and permission model. How do we implement security on a per-device basis? But there's actually a lot about Android that happens even before code gets to the device. Take the classic example of malware, and Andrew already talked a little bit about malware and whether malware is an actual problem or not. But to actually get malware onto the device, you actually have to go through a lot of different layers before you even get code execution. Google Play is the first line of defense for users. We're constantly reviewing apps. We're constantly making sure that apps aren't exploiting security vulnerabilities, aren't doing something bad. We're watching out for the user's best interests through Google Play and making sure that the apps are consistent with our policy. But of course, Android is an open system. We want to make sure that people have choices about where to get applications. So we allow sideloading. But even to get to sideloading, you have to go through, click a dialog, do you want to allow sideloading? We make sure the user is aware of the potential consequences. But even then, we rely on multiple layers of defense. So if you go to sideload an application, which we know to be dangerous, we will inform you about what's going on. We'll allow you to make a choice. And so one of the important security characteristics I'm sure everybody in this room is familiar with is the principle of defense in depth. We don't rely on any one security control to implement the security features of Android and keep users safe. Most of my presentation today is going to be on the lower right-hand corner, the security runtime checks and the sandbox and permission model. In my mind, Android, there are 4 pillars of security. Whenever we look at a security problem, whenever we look at a security bug, we try to answer 4 questions, 4 goals. How can we prevent the bug from happening in the first place? The best security bug is the one that can never happen. Can we pull the battery from the device? Well, that's not a practical solution. But are there other changes that we can make? We know that prevention is going to fail at some point. So we fall back. Layers of defense, layers of defense. Detection. Detection is a valuable tool that we have in our tool set. Are there things that we can do to increase our knowledge about security bugs, to make sure that we're aware of what's happening on device? Minimization. We know there's going to be security bugs. What can we do to make those security bugs so they don't compromise the entire system, so that the process is contained, so that we understand the characteristics when something bad happens. And the reaction. What do we do when something bad happens? How do we address it? I really think any security organization needs to have answers for these four questions, for these four strategies. I want to go through what Android's answer for these four strategies are. So the very first pillar of Android security is prevention. We want to make sure that we prevent bugs from happening before the user even has to think about it. Hopefully the user doesn't have to think about it. Hopefully it's the people in this room who are thinking about it. Android does all the traditional approaches to security prevention that you'd expect from any mature security organization. Code audits and code reviews. All of Android's code is peer-reviewed by another engineer within Android. We make sure that code that's being checked in, regardless of the source, has a second set of eyes on it. For code that's especially security sensitive, we'll have security teams which take a look at it, make sure that there's no problems with the code, or at least no problems that we can find. Make sure that it's consistent with what the security best practices. In addition to code audits, design reviews. Does the feature make sense? Is the feature going to cause security issues on the device? Is the code going to violate the user's privacy in some way? A big focus of our security team is on outreach and education. A lot of times we act as an internal consulting organization for other people who are implementing security features. And so we want to make sure that they have the tools that they need in order to make good security decisions. One of the things I'm very proud about with Android is we adopt a safe by default design philosophy. Applications, I'm going to talk a lot about our sandbox model, but applications have to go out of their way to introduce security holes. If you're an application developer and you just write an Android application, your application should be safe by default. There's also red teams, so we look at Android from the attacker's point of view. How can we break into Android ourselves, assuming you have full access to the code and to the engineering staff? So these are all really good traditional aspects of what you find in a security organization. Anyway, this leads me to lesson 2. And this is what I really want to spend a lot of time on, because I think it's confusing, and maybe people in this room may be familiar with it, but I want to make sure that more people are familiar with it. Lesson number 2, always start with a sandbox. If you're doing security engineering and you haven't used the term sandbox, you've made a mistake right off the bat. Android, from its very early days, was designed with the concept that we are going to sandbox applications. We are not going to allow an application to have full administrator access, full root access. We're going to have a discrete list of things that an application can do. And so this was a very important security property that was pretty much in Androids from day one. I'd like to take credit for it. I can't really take credit for it. But when we talk about the security of Android, a big chunk of the security relies on the sandbox itself. So Nikolai talked a little bit about the sandbox. I wanted to give a different view of the sandbox from the point of view of an early Android system. Android itself has always been divided into multiple different components. We have this concept of the system, which is responsible for mediating communication between different processes. We had this concept of root, which a lot of tools and resources would be running there. It's the root that you find on a traditional Linux system. And we also invented this concept using UID separation of multiple different sandboxes. Each application has their own home directory, their own isolated sandbox where they can run their code safely. So this was a very traditional Android security model for for older devices, 2.3. And so over time, we watch the attacks that are going on out there. We know what's happening in the ecosystem, and we're continuing to evolve the platform to make it more and more secure. In Android 4.1, we did a significant change to our security model. We now have this concept of multiple users, an enterprise space, if you want to, where not only were we dividing code up based on the application itself, we had this concept that multiple different users could use a device, and that one user's data would be protected from another user's data. So again, a refinement of the sandbox model. We also started introducing hardware roots of trust zone, and trying to move things, move especially security critical code into a place that would be unaffected by kernel vulnerabilities, that would be unaffected by other attacks against the system. And so this is good. I mean, we continue to evolve. This is the state as it was in 4.1. But we continue to look at attacks. And, you know, I was having lunch today, and they were talking about, you know, when is my job going to be done? And I don't think there's always things that we can learn from. There's always new attacks. So the next lesson I wanted to convey is we need to evolve. We need to continue to improve things over time as we understand new threats and as we're able to react to new threats. Android 5.0 was what I consider to be a very revolutionary change within Android from a security perspective. Android 5.0 was the very first release where we had SE Linux in enforcing mode. And so what happened? A lot of the components that were big monolithic components before became much smaller monolithic components. We were able to take each process and identify a set of rules, a set of SE Linux policy, a set of sandbox that we want to surround those processes with. So you have each one of those green boxes, but each one of those green boxes has access to different resources. Each one of the green boxes and red boxes have access to different bits of data. Another fairly revolutionary change that we made was in 5.0, we basically got rid of the root user. With SE Linux policies, there is no all-powerful God root user. You have a bunch of UID 0 processes which have access to certain resources. They could have certain, the typical DAC permissions that you might see. But the concept of root in an Android 5.0 device is gone. And so we have a lot of segmentation, and each one of these UID 0 processes, each one of these system processes has the minimum capabilities that it needs to perform its job and no other. And that's all the way down to almost everything that spawned from the init service, including shell scripts, including other things like that. So around the 5.0 timeframe, actually, I think Paul was involved in this, with this Reddit conversation. There was a Reddit AMA by John Sawyer, just in case, you might know him from the Android rooting community, where somebody asked him a question. Which Android devices do you find to be the most secure devices? And he said something that was, that made me feel really happy. In Android 5.0, the devices are actually very hard to root because of the SE Linux security policy, because of the tightening changes that we had. There may still be bugs, but we're able to make reasoned arguments about what the containment model is, what the security properties of the device are. So a lot of times he'd be aware of bugs, but he wouldn't be able to turn them into actual exploits, which is, you know, I talked about the different strategies for Android. It's really one of the things I want to see. So as we're continuing to move forward, you should expect these boxes to get smaller and smaller. As we further refine things, as we further make sure that we're following good design principles, good design practices, following the principle of least privilege, making sure that we have really solid architecture, these boxes are going to get smaller. And in the future, what we're looking for is more kernel protection features. We would like to, the kernel is a lot of the security controls that we have in place, Self-protection features for the kernel are an important research topic. Similarly, what are the things that we can do to reduce our reliance on code which is very large, which could have a lot of bugs in it, are the things that we can do more at a hardware level. So these are things that we're looking at for the future of Android. Similarly, there's been some research on supply chain because we're starting to see some supply chain vulnerabilities occurring where the devices are modified before they actually reach the end users. Strong security standards. So I think one of the important characteristics that we as security professionals need to do is make sure that we're providing guidance to the ecosystem about what is good security and what's not good security. In SE Linux, there's this compile time statement called never allow rules. Never allow rules are great because if you try, SE Linux is a mandatory access control system. If a rule doesn't exist, you just can't perform the operation. Never allow rules or compile time assertions that certain behaviors are not present. So what are some of the things that we don't allow on Android-compatible devices? No dev mem access, no dev kmem access, no ptrace of a init, no mapping at the zero address for kernel self-protection, no writing to the system file system. We talked a little bit about verified boot, but we also enforce this at the SE Linux level. Today we have about 250 SE Linux never allow rules, which not only are tested at compile time, they're also a contractual requirement that we have with our partners, that it is not permitted to modify this. They're CTS tested. CTS, for those of you who aren't familiar with it, stands for Compatibility Test Suite. It's the definition of what it means to be Android compatible. So as we discover undesirable behaviors in the ecosystem, we make changes to Android to address those undesirable behaviors and to make sure that we have consistent security policies across our entire fleet, our devices and our partners' devices. The second pillar, so I talked about the first pillar. It's very important to make sure that we're preventing bugs, make sure that bugs can't be introduced. But I also want to talk about the second pillar of Android security, minimization. Now, first of all, before I go into minimization, the sandbox model that we have for Android actually addresses both the prevention of bugs by making certain things inaccessible, and it also provides a mitigation. We know security bugs are going to happen. Everybody in this room knows that tomorrow or the next day, there's going to be another security bug. And so the sandbox allows us to understand the scope of what happens when a bug occurs. We know it's impossible to fix every bug. If it was possible to fix every bug, I don't think anybody would be in this room. And not only is it impossible to fix every bug, it's impossible to find every bug. As I mentioned earlier, there are thousands of people who are contributing to the Android open source project. There are thousands of unique devices out there, hundreds of manufacturers, all of which may not have security at the top of their mind, unlike the people in this room. It's actually like preaching to the choir. I really appreciate this. One thing that I don't think we do really well as an industry is to have robustness in failure. If you build a bridge, we were having this conversation at dinner last night. If you build a bridge and a car gets into an accident on the bridge, the entire bridge doesn't fall down. And so why are we at a state in software where one bug, one vulnerability can cause the entire system to collapse? I think it's a very interesting academic question, and it's very interesting from industry perspective why we haven't been doing more to have robustness in failure, to treat computer science as an engineering profession. Also, minimization maintains the integrity of the system. We want to be able to make reasoned arguments about the state of the system, even in the presence of bad or buggy code. So my next lesson today, account for human error. Everybody in this room makes mistakes. I've made mistakes that have had security consequences. Everybody in this room makes mistakes. We have to design systems that are robust against human error. So this is my pet peeve right now, so I'm going to chat a little bit about it because this has been the pain point of my last 2-3 months. Any mathematicians in this room? Anybody who got a degree in math? Really? No? Oh, yay, got one person. So mathematically, is this statement true? X plus 1 greater than x for all values of x? Should be. Okay, I'm not a math major, so I'll take should be as a good answer. I believe this statement to be true for all values of x, where x plus 1 is greater than x. Having said that, is that true in the computer programming world? No. 40 years ago, we as an industry decided that we only had a fixed space to put numbers in. And so what's going to happen if we take our maximum number that we can fit and add 1 to it? It's going to turn negative. This has been the bane of my existence. This decision that was made 40 years ago has been the bane of my existence for the last 2 or 3 months. It's important that programming languages reflect intuitive behavior and don't have really weird error conditions. And I hope as an industry, we can move away from this concept where numbers roll over. Anyway, programming languages have bugs. People introduce bugs. C is known for encouraging bugs. What are the things that Android does to help protect against bugs that may occur in the system? We have big protections like ASLR. ASLR has gotten a lot of press because of the recent stage fright vulnerabilities. It's a very important exploit mitigation tool. And I'll say mitigation because these aren't solutions to problems. These are ways to make it either more difficult to attack or shut down known vectors. Android from its very early days had no execute memory. Our stack is not executable, our heap is not executable. We've had that for a very long time. We enforce that on all Android devices. We have additional compiler protections called Fortify Source, which add buffer overflow protection to common libc functions. Read-only relocation stack canaries. We try to detect corruption of the state of the program and make sure that we fail cleanly because, again, we know that people are going to have buffer overflows. The last one is actually something I want to talk about. We are doing almost what I call innovations in the security space. Android is the first Linux distribution to completely ban non-pi binaries. If you are a dynamically linked binary, you will be randomized, and we guarantee that at the platform level. I'm waiting for other Linux distributions to catch up to it, to catch up to our sandboxing model and to catch up to our native code hardening and that kind of thing. I still wonder why Linux systems, you get access to the browser, you get access to all other data. But where are we going in the future? Like I said, we're never going to be out of a job. We have to do other things. Integer overflow protections. I actually think we need to move away from systems that have unknown integer behaviors. A big chunk of the stage fright vulnerabilities were because of this exact numeric property. CFI, control flow integrity, there are implementations that work today that have reasonable performance trade-offs. We need to figure out if these work and make sure that we're enforcing the integrity of make sure that we have compiler enforcement that if you call a function, you actually will get to that function, not to a different function. Stack protection and stack overflow. These are all areas that we're continuing to invest in and we're continuing to research in order to make exploits against Android harder. Which leads me to lesson number 6. Encourage safe languages. If you go leave this room with one thing, I want you to leave this room with the idea that if you write a line of C anytime in the future, you're making me sad because we need to, as an industry, we need to move away from languages which have known problems. Android actually did this. Android's primary development language, the one that we only supported for a very long period of time, is memory safe. You cannot perform a buffer overflow against Java. And it wasn't for a long time that we even allowed native code as an API. I mean, writing in a platform-independent language actually has a lot of other benefits besides just security. It also makes portability better and makes it a little bit easier. But even today, we specifically say that if you're developing a native code, you are a second-class citizen. We do not want to see like native code being ran. And so I think a big chunk of the changes that a big chunk of the reason why, a very important aspect why there's not more security vulnerabilities is because we've chosen as a development language Java. It was a very important decision that I'm really happy with. I mentioned this earlier, our industry needs to move away from unsafe languages. It's too risky, too error-prone. We need to figure out how we can get out of this situation that we're in today. We're doing research within our organization to try to figure out, are there tools and resources that we can make available to developers which are either a drop-in replacement for C or which can act in terms of C. They have the same performance characteristics. They have predictable memory allocation, deallocation. So I don't consider myself a language expert, and certainly if people had recommendations or suggestions on how we can dig ourselves out, we as an industry can dig ourselves out. I think it's a very important conversation to have. I'd appreciate it if you could reach out to me. Another thing which I think Android does well is this concept of principle of least privilege. Especially with the SE Linux implementation in Android 5.0, we've identified for almost every process on Android, what are the minimum requirements that it takes for that process to execute. And I think if you're doing security engineering, if you're a security professional, this needs to be at the top of your mind. And I've actually used this quote before, but one of the things that really strikes me about this quote is this quote's from 1975. I was only 2 years old at the time. I bet a bunch of people in this room weren't even born at the time. And so if you're designing a system that doesn't have the principle of least privilege in mind, then you need to reconsider that. So I talked about what's sort of the bane of my existence for the last 2 or 3 months. There was some recent press about a vulnerability called libstagewrite. And so there was a recent vulnerability called libstagewrite. And we actually designed the media server with containment in mind. And we also found that our exploit mitigations were really effective. An important part, the other principle I want to talk about is the principle of detection. It's not enough to actually prevent bugs. It's not enough to actually mitigate against bugs. You need to know that the bugs are there. So the next lesson is basically keep your ears to the ground. You need to know what's going on in the space. You need to know what the user's going. And how do we do this in Android? A bunch of different ways. We actually published from very early days our email address. So anybody in this room, anybody in the world who wants to reach out and talk to somebody on the security team can just email us. We have a bug database. We are consumers, readers of academic journals. We learn a lot of things from reading what the community is doing. We have automated detection of discussions in forums about security issues. And it raises our attention, and we're aware of what's going on there. A really interesting thing that I think we do is what I call failed exploit detection. When we fix a bug, not always, but a lot of times, we'll also instrument the bug. And we'll say, if this code path was taken, let's log it. Let's make sure it happens. So the devices that are fixed can act as protectors of the devices that are still vulnerable, so we can know what's actually happening in the ecosystem. It's a technique that not a lot of people seem to be doing today. We also have the Android Security Rewards program, where we are willing to pay money depending on the kind of bug that you bring us and the kind of help that you provide us in resolving that bug. Depending on how it's actually exploited, it could result up to like $38,000 in rewards. And I have a feeling that this number is actually going to have to go up over time. I have a feeling this number is actually too low. Fourth pillar of Android, reaction. It's important for any manufacturer, any operating system, any person who's doing software development to figure out how they're going to update their software. For Nexus devices, we've committed to a monthly security upgrade cycle. We make sure that we have public bulletins to know so people are aware of what the security issues are facing. And we've committed to doing this for 3 years from device manufacturer. And not only do we do updates for ourselves, we also support 1.6 million apps in our Play Store. And when those apps have security issues, we provide a mechanism for them to update. And we enforce at the system level that if there's a security bug, we just don't allow those apps in play. Those apps will get fixed one way or another. And so we've identified a number of critical bugs in apps, and we are in the process of making sure that those apps get fixed. No such thing as perfect security. A lot of times when the industry talks about security bugs, they're like, oh, 100% of devices are vulnerable to this. I think that does a disservice to our community. I think it's really important to talk about accurate risk assessments. If you are in the medical industry, you wouldn't say 100% of humans are vulnerable to Ebola. You just wouldn't see a headline like that. And so there have been news headlines, 99% of devices are vulnerable. And these are actually numbers where we could actually measure them more effectively. We could actually have visibility about what APKs were being installed. And so when we actually started looking into this, there were bugs that had big headlines, but there were only like 1,200. This was this particular bug where there was a mismatch in the signature checking for APKs. And it turns out that the vast majority of people who were exploiting were looking for game cheats. And there was no exploitation in the wild. I do think as an industry, we need to have real information about risk and make sure that the information is available. Google is doing our part by publishing our annual security report, where we actually go into lots of details about what we're seeing in the industry, the exploitation we're seeing in the industry, to make sure that people have accurate information to which to make security decisions. Anyway, I've run over time. Android itself grew up in the internet age. We benefited from 40 years of experience. We actually have what I consider to be a sophisticated, robust security model, and we're going to continue to evolve. So, thank you. And I apologize for, how far did I go over time?
You're perfectly on time. So we do have time for questions. Please, shoot.
Yeah, hello. What's your opinion on using native code for security-related tasks, or thinking about the easy re-engineering possibilities of Java code, for instance?
Native code for security tasks. So I don't think native code should be used for a lot of different tasks. I would think that there has to be other languages to support that, but certainly if it's a choice between code that's already written and has been tested, I mean, I can see an argument for code that's already been written and tested where you already have an understanding of the security properties of the code, and you might introduce more risk by moving to a different language. I don't know if that, I think it would also depend on a case-by-case basis.
seen some examples recently of Android device vendors that have introduced careless security mistakes into their devices with the vendor-specific customizations. I was wondering if you had any thought on how to avoid those.
I did talk about what we're doing on the SE Linux side, called never allow rules, which enforce certain consistencies in the ecosystem. I think you're familiar with never allow rules. We also make sure that we publish best practices and guidance to our partners about what to do and what not to do. Part of this is an education process for them and for us, and making sure that enough information is available and enough testing is available to encourage correct behaviors and to encourage not introducing problems.
I have a tough one. How do you at the moment see any way forward concerning the patching, the updating problem with all those thousands of different devices, with the OEMs, the MNOs, in between the updates coming to the Google source tree and actually hitting users? What do you think? What kind of improvements would be the best way forward there?
I mean, that's a really tough problem. Certainly making sure that we have information available about which devices are updating, which devices aren't updating. Make sure that people have intelligent information in order to make intelligent decisions, I think is a really key aspect of trying to make sure that we drive updates, and as an industry, we encourage updates. The removal of code, making sure that we have mechanisms outside of an OTA to do security updates is also an important thing. If we can split more off from the core operating system. Android applications are a really great example of that, where the applications aren't tied to the system. They can be updated independently through Play Store. But I think just making sure we have more awareness is a really great step, and I don't know if there's any easy solutions.
Any other immediate questions? Yeah. I fear that has to be the last one, and I would like to table the others for the coffee break.
One question concerning privacy, because in the first presentation today we heard that there are many apps who are requesting too many permissions, and this is a major privacy issue. Where is the development heading in this direction?
So we've been primarily focusing development not at the platform level, but at the Google Play level. So every app that's hosted on Google Play is required to meet our standards, and applications which are extracting information from a device without the appropriate notification to the user are banned. They have to follow our terms of service, and they have to follow to be hosted on Google Play. So the problem is that this is one of those mixed cases where there's legitimate need for some of these APIs and for some of this data. You can't universally say this particular bit of data is bad. And so all of the apps in Google Play meet the terms of service. If they don't meet the terms of service, we make sure that they're removed from Google Play until such time as they do meet the terms of service.
Because I found it interesting, because security-wise, I'm with you, because you said one of the design goals should be that the user feels that there's some calm state evoked, but on the other hand, in terms of privacy, users should be more aware of what's going on, and so maybe there's some discrepancy here.
It's a tough challenge. I mean, I allude to this on one of my very early slides, that there's a balancing act between functionality and security. One of the things that we did for Android M was to introduce user promptable permissions, or a permission model where we actually disclose to users at the time of use that a particular operation is being allowed, which I think will give users more control over how they want to share information. A lot of people are perfectly happy to share information, and we need to make sure that there's visibility into that.
Okay, thanks.
Thanks again.